So I'm going to be going over the study guide for the part 1 test over chapter 6. Okay, so for the first one, describe the energy transformations in the scenario. So on August 6th, 1945, an atomic bomb was detonated over the city of Hiroshima, Japan. Witnesses reported a blinding light, searing heat, followed by a loud explosion that blew out windows. Okay, so the first thing that we started with was the atomic bomb. Because it is an atomic bomb, this is going to be nuclear. Okay, but just as a note, generally other fuel, okay, such as gasoline, the food that we eat, wood, it is going to be chemical. Okay, same thing with like batteries. We talked about stored energy, that is chemical. Okay, if we look, the next thing is that the eyewitness reported blinding light and searing heat. Okay, so the nuclear energy was converted into light energy, which is radiant energy, and then the heat, which is thermal. All right, and then finally it says it was followed by a loud explosion. Okay, this would be sound. Remember that sound energy is a mechanical wave, so it is mechanical. Okay. For question number 2, what is the difference between complete and incomplete combustion? Okay, so I'm just going to use methane, and it kind of goes into question number 3. So methane, CH4, reacts with O2, and it's going to yield CO2 plus H2O. Okay, and this is for complete. All right, just some other notes on the complete combustion. Okay, the flame is going to be a pure flame. So if you think about like turning on a stovetop, you'll get that blue pure flame with no smoke. Okay, so the reactants for the complete combustion is CH4 and O2, and then the products are the CO2 and the H2O. Okay, so with complete combustion, there's enough oxygen in order to create the carbon dioxide. For incomplete, again, we'll do the combustion of methane. If there's not enough oxygen available, what will happen is the products will be, instead of carbon dioxide and water, will be carbon monoxide, and water vapor. Okay, so for this, the flames are going to look different. It's going to have orange flame. And due to the carbon being produced, it's going to have black smoke. Okay, so we see this with like house fires. Because there's not enough oxygen available to the flames that are inside of the house, it creates these great big orange flames with the black smoke. Okay, so with the equation, let me change colors again. This side is our reactant, and then this side is our product. Okay, so the key things with that, the reactant is always going to be on the blunt side of our arrow, our yield arrow. Okay, and then the product is always going to be on the pointy side of our yield arrow. Okay, what is the law of conservation of matter? It's just that the reactants are going to equal the products. Okay, as far as the mass and the matter. Okay, so whenever we look at, for example, we looked at balancing equations, okay? We need to make sure that the same number of atoms are on both sides. That would be making sure the law of conservation of matter is being watched after, or we can have mass. So for like question number 5, if we have 10 grams of a reactant, we would expect to have 10 grams of product. Okay, for balancing the equation, I believe I have 3 of them in the test. Okay, the way that I go about doing it is I split both sides. I write out the elements that I have. Right, I count on both sides. So I have 1, 3, 2, 1, and 4. And then for this side, I have 2, 1, 1, 3, and 12. Okay, so I'm going to start with iron. I have 2 on the product side and 1 on the reactant side, so I need to multiply this by 2, so it's going to change this to 2. My bromine is now 6. Okay, so if I need to match my bromines, that means I need 6 on the product side, so that's going to change my H to 6 and my bromine to 6. Okay, now looking at hydrogen, I have 6 on the product side, 2 on the reactant side, so I need to multiply my reactant side by 3 in order to change it to 6. My sulfur is now 3, and my oxygen is now 12, and if I look, I have equal amounts of each element type on both sides. Okay, for the second one, I counted out all of my different elements. Okay, so my nitrogens match, my oxygens match it, but my hydrogens do not. Okay, and so for this, what I need to do is find the least common multiple for them. Okay, which in this case would be 6. So I would need to multiply this side by 3 and this side by 2 in order to come up with the least common multiple that they have of 6. Okay, so now recounting each side, I now have 2 nitrogens, 6 hydrogens, still 2 oxygens, and then for this side, I now have 1 nitrogen, 6 hydrogens, and then for oxygen, I have 3 plus 1 is 4. Okay, now I need to balance out my nitrogens. So I have 2 on my reactant side and 1 on my product side. So I need to multiply it by 2. So now I have 2. And then as far as my oxygens, I now have 5 oxygens on this side, and I have 2 oxygens on the reactant side. So in order to get this oxygen here to be 5, I can multiply it by 2.5. Okay, so now this would be 5 on this side. I am balanced, but I cannot have a decimal as a coefficient out in front. So I need to multiply all of my coefficients by 2. Okay, so this one is going to become 4. This one will become 5. This one will become 4 and 6. For the last one, what are the 3 components of fire and how can they be manipulated to put out a fire? So if you remember from class, we have our fire triangle where our different aspects are fuel, oxygen, and heat. Okay, so ways that we influenced or manipulated the different aspects in order to put out the flame. I didn't show this in class, but I could have used a Bunsen burner. Right, and with the Bunsen burner, if I turn off the gas, it's going to stop the supply of fuel and put out the flame. For oxygen, we can cover the flame in order to cut it off from its supply of oxygen, or like the demonstration that I showed in class, I can use CO2, okay, which is more dense and would cut off the oxygen from the flame. And then the heat, I used the copper wire to steal the heat or absorb the heat away from the fuel or from the fire source, which caused the flame to go out. But when I removed it, it did come back.